So for our last bit, for section 7.1, 7.2, we're going to find values from a normal distribution corresponding to a given proportion. So everything we've been doing so far is we've been going and finding that proportion or probability. Now, this time you're going to be given that proportion or probability, and you have to go backwards and figure out what the value that is associated with it is. So we did a little bit of this before. So back when we were in, I believe, chapter 3, and we were doing z-scores, we had this kind of problem. Suppose we want to find the value for a normal distribution, find a value from a normal distribution that is a given z-score. To do this, we saw the standard normal formula. Let me circle that a little better. There we go. Which is my z-score, x minus mu over sigma equals z. We go and we solve it for x. So if we want to find a value for x that corresponds to a given z-score, we need to know what that mean and standard deviation are. But what x would be is the mean plus the z-score times the standard deviation. Like I said, something very close to what we did before. Heights in a group of men are normally distributed with a mean of 69 and a standard deviation of 3. We want to find the height whose z-score is 0.6. So right here, we're trying to find this particular height. This is the x I need to look for. So x, that particular height, mean plus z times sigma. So we got 69. We got a z-score of 0.6 times 3. So I'm adding on 0.6 standard deviations to my mean to find this person's height. And what we're going to get, sorry, the calculator was slowing down there, times 3, we should end up with 70.8. So 70.8 inches is associated with a z-score of 0.6. All right, so let's actually do some application here. So z-scores from areas. We have been finding areas under a normal curve given a particular z-score. Many problems require us to go in the reverse direction. So that is, if we are given an area or a probability, we need to find the z-score that corresponds to the area under the standard normal curve. It is useful to remember that the mode is going to be 0 and has an area of 0.5 both to the right and left of your z-score. Basically saying this. This is the center of my distribution. That means as far as in z-scores, the mean is 0. This area here is 0.5, and this whole area here would also be 0.5. So it splits the area into equal halves. And so we're going to need that when we start kind of thinking about z-tables a little bit, about what we're really looking for. So suppose we wanted to find the area of 0.62 that is to the left. So what we're saying here is that there is some sort of mystery z-score that separates this lower part of my distribution, this 0.26, from this upper part. So remember, we are below the mean. So that means that we're be looking at the negative z-scores. So in this case, we're not looking for the z-score, or sorry, we're not finding the z-score on the chart. And finding an area, we're finding an area and then going backwards and finding that z-score. So the area to the left, because that's what z-scores are telling me, always area to the left, is going to be a 0.26. So what I need to do is go into my table, and remember, these are all different areas. So this is the area if, right here, if my area was instead 0.26, 2090, like this does, that's telling me that the z-score that marks that off is a negative 0.81. Our problem is we don't have something that's very, very exact. The area that we're looking for has to be as close as we can get to 0.26. So there's going to be a lot of estimates when we're using our z-tables here. So we see here, I got 0.2643, well, that's kind of close. I got 0.2611, that's even closer. And I have 0.2578, that's also close. So what we were trying to look for is which one of these is the closest we have to 0.26, which would just happen to be, of course, the one in the green that's highlighted, 0.2611. So this is as close as I'm getting to 0.26. So what I'm really looking at here is that I have an area that is to the left of some particular z-score, and that area is 0.2611, not just 26. And what I need to do is once I find that area, I go back and I find that z-score. And it's telling me my z-score is negative 0.64. Just combining those together. So we're going to also make the assumption that the area to the left is, like I said, the area to the left is 0.26. So as close as we can get, this is as this area. So we're going to say, so the z-score is also going to be negative 0.64. Like I said, it's as close as I get. It's an estimate. It's as close as I'm probably going to get. And we probably should just say z is approximately negative 0.64. So let's say we're looking for an area to the right now. So if you remember, once again, that what z-tables do is they always tell me area to the left. But I want to find the z-score of an area of 0.68 that's to the right. So I have to go back and I have to do my conversion here. So we have some mystery z-score here, same mystery z-score here. If on this side we have 0.68, then this side, the side that I'm going to need to use for my z-table, well, that's going to be 1 minus 0.68. So that's going to be 0.32. So we're going to go back into the table and get as close as we can, looking at my areas, finding an area as close as we can to 0.32. We got a 3.228 here, and we have a 0.3192. The one that is closest to 0.32 is this one. This is only 0.0008 away from 32. This one is 0.0072 away. So like I said, we're looking for the ones the closest. So if I go backwards from there, we're going to get that this z-score is negative 0.47. So always remember, you always have to find area to the left if you're going to use a z-table. So the area to the left of 0.32 and the area to the right of 0.68 are broken apart by the same z-score. It's going to be that negative 0.47. Now, if we're trying to look in between two scores, once again, we have to remember that what we're trying to do is we're just constantly trying to figure out the area that is going to be to the left, because that is what a z-table is going to give me. So we want the z-score for that bounds the middle 95% of the area under the standard normal curve. So what we want is that this, let me get a brighter color, this exactly in the center is going to be 0.95. What that means is that the area that I have in this curve, this tail and this tail should be equal. So area and tails Remember, 1 represents everything, but I'm taking out that 95 in the center. So the area left in the tails together is 0.05. That means each tail has an area of 0.025 divided by 2, because we got two tails with an even area. So that is going to be 0.025. So each tail has an area of 0.025. So I'm looking for 2 different z-scores because I'm trying to bind an area in the center. I'm not looking strictly less than or strictly greater than. I'm looking in between 2 scores. Let's try to get my green back here. So what I'm looking for, if I want my z1, is I need this area that is to the left using my z table. So that is 0.025. If I need my z2, remember that what's in this tail is 0.025. So what's left here is going to be 1 minus 0.025, or 0.975. All right, so we're going to bring this to the z table, and we're going to figure out what those 2 z-scores should be. So we need to get as close as we can to 0.025 to find z1. So we're looking for that area. Remember, we're going backwards to find that z-score. So be careful with this one because we have a tendency to forget how many zeros we need to go out. And you might be tempted to go, hey, right there, that's my 2.5. Well, that's 0.0025. So not quite what we need. What we need is going to be right here. So this is one of those few cases where we find exactly that z-score. If we go up, what we see is that this z-score is negative 1.96. All right, so next we have to find my z2, and the area to the left of z2 was 0.975. So you're going to notice something here. Hopefully we notice something here. So as we see, this is all less than 50% because it's below the mean. This is everything that's going to be greater than 50% because it's above the mean. So we're going to look up here. And right here we have 0.9750. So 0.975. Well, that z-score is going to be 1.9. And we need that last bit. So let's scroll up and see where this arrow takes us. It would take me to 6 again. So if you notice on both sides, we're getting the same z-score. It just has a, well, same magnitude, but one is positive and one is negative. And this is a common thing because our tables are symmetric, or our distributions are symmetric, should I say. So if I take out 95% in the center, then what I should have here is a z-score, and here's a z-score. Like I said, are always going to be equal in magnitude, but one's positive and one's negative. So it doesn't matter what it is in the center. All I know is that if I find this z-score here, they're going to be the same z-score, just one's positive, one's negative, as long as we take it out exactly in the center, because we should have the same area in both tails. So this is a common feature that we're going to see going forward, especially when we start talking about confidence intervals. Okay, so we are going to go through our steps here of finding the normal value. So first thing we're going to do is we're going to sketch that curve. It's always helpful to sketch pictures of our curve. So sketch our normal curve, label the mean, label the x value to be found, and shade in the label that gives the area. If the area is to the right, then we subtract 1 to get the area to the left. And we look in at the table, so those z-score tables, and what we're going to do is we're going to find the area closest to our given area, go backwards, find the z-score. And this is a step we haven't done so far because we haven't actually looked for x, except for the one case, we're not finding those z-scores. Once we obtain that z-score, then we can use that x is equal to mu plus z times sigma to go back and find the actual value that that area is associated with. So we're going back and finding an actual x value. So scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. We want to know what score separates the upper 2% of IQs from the lower 98%. So we got the picture here, but really what we're saying is we're looking for something that splits the upper 2% from the bottom 0.92 or 98 or 98%. So together that makes 100. So we're looking for a z-score here so we can go backwards and find an x score. So this is what we're going to end up looking for, as we know the mean is 100, and I'm looking for an x that is going to be up here. But like I said, the side step to getting to this x is I need to look at this as a z-score first. So what I'm really going to do is in the Maze table, is I need to find this area, even though what I'm really interested in is my upper 2%. We're going to look for this lower 98% first to get that z-score. So let's go to our table. Okay, so like I said, we need to look for that area that's to the left of the z-score, even though we don't know what the z-score is. So we're looking for the area of 0.8, no, I'm sorry, 98. So we go in here and look for as close as we can get to that. So it's either here or here. So this is 9798, this is 9803. So we just need the one that is the closest. So this is 0.0003 from the 0.98, and this is 0.0002 from the 98. So this is my closest. Okay, so I'm going to do a little adjusting here. Now that I found it. And now I got to find it again. There. So that's one of the hard things about Z tables is because the numbers are so clustered together and so many of them are so close when you're trying to go backwards and find those areas, you can get a little lost. So that's something to always be careful of. That's why I usually suggest using the TI-84 or any kind of technology because that just makes this a little easier to do. You make a few less mistakes. But right now we're working on the Z table. So if we go backwards and we try to figure out what that z-score should be, what we're seeing is that my z-score should be 2.05. So remember, you're adding the 2.0 to the 0.05. So we get 2.05. Okay, so now we got the z-score. Let's go back and actually solve our problem. Okay, so just as a reminder that these two distributions are showing us the same thing. Just this one is all z-scores and this is all x values. So we found everything according to z-scores because that's what z-tables will give me. Now I'm going to go back and actually find my x value. So remember, if we want to find x, that is just the mean plus the z-score times the standard deviation. So for IQs, where mean is 100, and then our standard deviation is 15. Our z-score, so if we were trying to find that score that splits the upper 2% from the bottom 98%, we got approximately 2.05. So it's just a little over 130. Let's figure out exactly what it is. we are going to get an IQ of 130.75. I'll probably say 131. All right, so that is my IQ that separates the bottom 98% and the upper 2%. So I had to stop for a second to look it up. So 130 is actually the benchmark. Above 130 is when we start considering somebody to be moderately gifted. So that's part of the reason we picked this 2%. Like I said, that the 2% is because we're trying to pick a spot where we're saying like 2% of the population should be moderately gifted. And we went back and figured out what the Z-score is to mark that boundary. But that's how we do a lot of the boundaries of IQs and things like that, as we make decisions about what percent has what significance, and we go backwards and we figure out what range of scores would give us that. All right, so here we want the IQ as normally distributed with a mean of 100 and a standard deviation of 15 still. This time we're going to find the IQ that separates the middle 90% of scores from the top and bottom 5%. So kind of go through what this means again. So we have a distribution, and what we're taking out of the middle this time is my 90%. So we're going to get, when we look at the Z-scores, a Z-score here and here, so they should be the same Z-score, just one's positive, one's negative. But to figure out what that Z-score would be, we need these areas here. So 1 represents my whole distribution. If I take off that 90%, I am left with 10%. That's going to belong into the tails. If I split that evenly between the tails, then we're going to get 5% or 0.05. So this is the area in each tail. So we know that here is 0.05 and here is 0.05. And like I said, we're not going to go through and find two Z-scores because all I need to do is find that one, and we know that's going to give me the other score. So I just need to figure out what Z-score is associated with 0.05, or an area to the left of the Z-score of 0.05. All right, so like I said, we just need these two Z-scores, but I just need to figure out this one area. So I need to find my 0.05. So if you notice here, this is all above 0.5. So I need to go to the other side. And I'm looking for the area in here. And once again, be careful that you're rounded out to the right amount. You have the right amount of zeros before your number, because you might be tempted to go through and go, oh, right there's my 0.5. Or you might be tempted to go here and go, oh, there's my 0.05. We're looking, like I said, make sure that it is actually a 0.05, not a 0.005 or 0.0005 or a 0.5. You want to make sure you get the right decimal places out. So what we're looking for is right here. So in this case, we have 0.0505 and 0.0495. Both of them are equally the same distance from 0.005. So what we're actually going to do is we are going to take two Z-scores. So for an area of, got too many decimal places there, 0.0505, that Z-score is going to be negative 1.6. There we go. Sorry, my thing is up here. There we go. So we're going to have that 0.4. The area to the other side, the area of 0.0495, that's the score as we see. It's going to be almost the same, except that it's going to be negative 1.65 instead of 64. So both of these areas, flank both sides of this. Not one of them's closer than the other. So what we're going to use for z-score, so this happens if it happens to fall exactly between two values, the z-score of an area. Is going to be, we're going to take the one z-score, we're going to add it to the other z-score. So we're going to average those z-scores, divide by 2. So we're going to get a z-score of negative 1.645. So what that means is that this z-score is going to be negative 1.645, and this z-score is actually going to be the positive 1.645. So that is going to bound both sides of that 90% in the middle. So we have those z-scores, we can go back and get our x value. So we know that if we're looking at this as just z-scores, we got the 0.9 in the center, leaving 0.05 in both tails. The z-scores we're going to have that binds this 0.9 in the center is going to be z1, which is negative 1.645, z2, which is positive 1.645. So we're going to associate it, like I said, we're trying to associate with this over here where everything's in x values. So I need to figure out two x values. I need my x1, which is going to be my mu plus z1 times sigma. And then my x2, which is going to be mu plus z2 times sigma. So mean IQ is 100. We got a z-score of negative 1.645 times a standard deviation of 15. Over here, we have 100 plus a positive z-score of 1.645 times a standard deviation of 15. So the x values are not going to have like the same x values, one's positive, one's negative. It just happens with the z-scores. Oops, what we're going to get is, these are both equal sides of 100. We're going to get 75.325, and then we'll have over here 124.675. So if we were round these to closest to where they are supposed to be, this is like 75, and this is 125. And actually, this is a range that sometimes we consider the range of normal IQ. So what we know is that from looking at the middle 90%, that means that 90% of my IQs of 90% of IQ scores are between about 75 and 125. But once again, like I said, we decided that 90 should represent basically what is normal. So we go backwards and we try to figure out this range of what's considered a kind of normal IQ. There's a little bit of your bright IQ in here as well. But past this mark is when we start considering having a disability. Usually, like I said, the scores kind of vary sometimes, but typically this is the side of disability and this is the side that's gifted. So it's marking those boundaries of what we consider gifted and what we consider an intellectual disability. Once again, that's all based on going, we think 95% in the middle is basically what's considered normal. All right, so practice this one more time. So we're going back to those dogs. That's the mean lifespan of a dog is 13.42 years with a standard deviation of 2.36 years. We're going to assume that lifespans of dogs is normally distributed. We want to know what age separates the bottom 5% of the lifespans of dogs. So we're going to bring this all to a Z table. So let's break down some of our information over here. So what A is looking at is we're going to have our distribution, and we're looking for our bottom 5%. So this area here should represent 0.05. So this one we kind of know already because we found a Z-score for that. So we want to know what age separates that. B is going to be what separates the top 15%. So we're looking for an X here. And what we're going to look for here is that this area is going to be 0.15 for that 15%. And then C is the middle 95%. And 95 is another one I believe we had found already. So this requires me to find two X values, one on both sides of that middle 95%. So like I said, it's that middle 95% breaking you from the top score of 2.5 in the bottom and the top. So we don't have to find this one again. We already found it once already, but that's what's in those two tails. Okay, so we're going to bring this to a Z table. Just a second here. So A is going to be the easiest for us because I don't have to do any conversions for A. I just need to find that 0.05. Like I said, we had already found this once, but kind of go through that again. So we found these two scores in the center that are as close as we can get to 0.05, and they're both equal distance. So we ended up, make myself some room over here. I know you guys don't see anything, but there's tons of stuff on my screen on the side. So for A, the z-score that we're going to have is going to be that average of the negative 1.64 and the negative 1.65, which is going to be a negative 1.645. So that tells me my z-score. So the z-score I associate with this x value is negative 1.645. So for dogs, remember that the mean lifespan of a dog is 13.42 with a standard deviation of 2.36. So the age that splits my bottom 5% of dogs' lifespans is going to be, 13.42 plus my z-score of negative 1.645 times my standard deviation of 2.36. So what we're going to get here, 13.42 minus 1.645 times 2.36 is going to be 9.4378. So we could round this and say 9.5 years. This is approximately 9.5 years. So 5% of dogs are probability that a dog only lives for 9.5 years. It would be that 5%. Kind of going back to those probabilities of what these are actually meaning. Okay. So I'm going to use red and I'm going to put B right under this. So B, we're looking for we're looking at for the age that splits my top 15% of lifespans from dogs. So we have my 0.15 here. That means this area here, which I need for my table, is 1 minus 0.15 or 0.85. Okay. So I need to find this. That's the area I'm looking for, my 0.85. So let's scroll down until we find it. All right. So right in here, we got to decide what looks closest. So I would say it would be, this is my closest to 0.85. We got 0.8508. So if I go backwards, the z-score that is associated with that is going to be 1.04. So we know the z-score, we just need to go back and get that x value. So here, x would be 13.42 plus 1.04 times 2.36. Oops, put my decimal in the wrong place. It's getting the wrong answer there. So this would be an age of 15.8744. Let's round that to just say 16. Everything's rounded anyway. So we're going to get different numbers later because we're going to do some TI-84 as well, just to show you how that works. So my x here is roughly about 16. If you wanted to, you can say 16 or 16 or 15.9. So that would mean that the probability that a dog lives longer than 16 years is about 15%, 0.15. All right. So for my very last one, I erase a bunch of stuff over here. It's going to take a little bit more room from us because we need to do two things. Well, one, we need our area, but we were kind of already given that by the way this question was structured. So remember, this is that 95 exactly out of the center. So my z-scores are going to be equal. It's just one's going to be positive and one's going to be negative. So equal in magnitude. But anyways, we were told that this area is 0.025. So we just need to find that area. And this is one of those ones where lucky happens to be exactly on here. There's not really much guessing going on here. So, but we get that my Z1 on the side is going to be the negative 1.96. That means that the other score has to be the same magnitude. It's just going to be positive. So Z2 would be 1.96. So the lifespan of my dogs, we're going to have an X1, which is going to be using my Z1 here. So that's going to be my 13.42 plus my z-score of negative 1.96 times my standard deviation of 2.36. And then we have x2, which is going to be 13.42 plus the z-score, so now positive 1.96 times my z-score of 2.36. Bear with me just a quick second while I get this in here, 96. So this is going to be 87944, and the other one will be, there's no rule in reasoning to how I'm rounding right now, just so you know that. I'm just sort of kind of rounding. So I'm just rounding to years for the most part. This is about 9 years, and this is about 18 years. So this means that the probability that a dog is going to live somewhere between 9 and 18 years is about 95%. Just 95% that any dog I get is going to live somewhere between 9 and 18 years.